Okay, so we're going to finish with the second example that we were starting in class on beta decay. So for the second example, let's consider beta decay. So we know beta decay is really just a positron or an electron. So this could be beta plus or beta minus. So let's consider a beta minus case. So let's say we have a neutron that's decaying into a proton plus a beta minus plus a anti-electron, so an anti-electron neutrino. So we have a new anti-electron neutrino. So that is the decay. So what would the Feynman diagram look like? So once again, that we have space on our x-axis and time on our y-axis, which I know is a little funny. And let's say the neutron was stationary, so it's staying at the same location. And at some time, some undisclosed time, it is going to give off a proton. Okay, so it's going to turn into a proton. Now, you have to ask yourself, what is responsible for decay? What is the force carrier for the decay, the weak nuclear force? So for the weak nuclear force, we have the W minus, the W plus, and the Z bosons. So we know that there's going to be a decay of some kind. And the question is whether it is going to be a W plus, W minus, or Z boson. So we're going to actually use some conservation laws to figure that out, and specifically the conservation of charge. But we know that it is going to send out a W boson, or sorry, a boson of some kind, and it is going to create a beta minus, so an electron, and a anti-electron neutrino. So there's that. So now we can use conservation of charge, and if we focus on this one vertex right here, so looking at that one vertex, we have zero charge coming in to it, we have positive charge coming out of it, so we need to have negative charge coming out in order for the conservation of charge into and out of that vertex to be the same. So if we're looking at these three bosons, we have a negative charge, we have a positive charge, and we have zero charge. So we need to use the W minus, so we can actually tell that that decay process will occur based on through the W minus mechanism in order to create the beta particle and then the electron neutrino. So if we check, we also could do a little check of lepton number. So let's look at our lepton number for each of the two vertices. So lepton number here, that's not a good color, let's use green. So lepton number here is 0, because the neutron is not a lepton. The proton is also not a lepton, okay? And the W minus is also not a lepton. So in terms of the vertex on the left-hand side, this vertex once again, we have 0 in and 0 plus 0 out. And so the other vertex, so the one over here, we have 0 in, so we must have 0 out. So since the electron is a lepton, it has a lepton number of +1. And the anti-electron neutrino is an anti-lepton, so it has a lepton number of -1. So we have 0 going in, we have +1 and -1 going out, so lepton number is also conserved. And then baryon number, let's see if we can see blue. So baryon number in blue here, for a proton is a baryon, so it has a baryon number of 1. A neutron is also a baryon, it also has a baryon number of 1. And then the W boson is not a baryon, so it has a baryon number of 0. So we have 1 into the vertex on the left, and we have 0 and +1 out. So 1 equals 1, baryon number is conserved. And then the vertex on the right, this one once again, it has 0 baryon number coming in, and it has two leptons, or a lepton and anti-lepton coming out, and they both have 0 out. So 0 in, 0 plus 0 out. So both of those are conserved. Some notation that the IB sometimes will put in a diagram is if we focus on this section right over here. Let me put this in a different color here. They may show that section, if I zoom that in over here, they may show that section as the electron going in that direction, and they may show it as a electron neutrino, but the arrow goes in reverse. So if the arrow goes in reverse, they're talking about the anti-particle. Okay, so notice that they won't have the bar over it and the arrow going backwards. They'll either have the arrow going forward and the bar on it, or the arrow backwards with no bar. But either way, it's the anti-electron neutrino. All right, so one more example, and then that will be all. Let's think of a positron decay. So a proton that is decaying into a neutron plus a beta plus particle, and since this is an anti-lepton, then this will be an electron neutrino, not an anti-electron neutrino. So take a minute and pause the video and try to do this Feynman diagram. Okay, so let's take a look at what that Feynman diagram would look like. So we have space on the x-axis, we have time on the y-axis, we have a proton that is stationary coming into the vertex, the first vertex, and it's decaying into a neutron. And the messenger particle for that decay must be a W minus, W plus, or Z boson, which we'll decide what that is in a moment. We have a positron, a beta plus particle, and then it is also a electron neutrino. So we have +1 coming into this vertex for charge. We have 0 coming out. So this tells me we need to have a plus coming out. So it's our W plus boson that is responsible for this decay. And you can go through and check all of your conservation laws. Try it for conservation of lepton number. Try it for conservation of baryon number, and then also for conservation of charge, which we already addressed the vertex on the left. But see if the vertex on the right also has conservation of charge. Just a couple little things. Generally, when we're talking about this exchange of either the W plus or W minus or Z boson or our photon, if we're talking about photons, we'll typically show the electromagnetic force, the photons, during this exchange as some squiggly lines. The WZ bosons will be a dotted line during the exchange. Notice I have the dotted line on the left-hand side here. And then the gluons, if we have some gluons, for the strong nuclear force, we'll show it as a bunch of swirls. So we have the strong nuclear force through our gluons, we have our weak nuclear force through our WZ bosons, and then we have our electromagnetic force through a series of photons. So that's the basis of Feynman diagrams. Obviously they get much more complex than this, but this should help you with the general gist of it. All right, thanks for listening. Have a good night. Bye-bye.